All right, so let's continue. How do we do the linearization of a nonlinear 2x2 system? So suppose you have a nonlinear system, x prime equals f of xy, y prime equals g of xy. And suppose AB is an equilibrium point and that means f of AB equals g of AB equals 0. So again, if that doesn't make sense, just pause for a moment and make the connection. AB, an equilibrium point, is a constant solution, so that means it will satisfy the whole system, and because it's a constant, x prime and y prime is equal to 0. So therefore it will satisfy f of AB 0, g of AB 0. Then we have the so-called Taylor approximation, Taylor formula, or to be more precise, the linear approximation of a function of two variables. Those of you who took calculus 3 will realize immediately the equation of the tangent plane to a surface given by a function of two variables. So the equation of the tangent plane to a surface at the point AB is another way of saying linear approximation of a function f of xy. So it's the same thing, but interpreted for our purposes as a linear approximation. So f of xy then can be approximated by the linear approximation of that function, which at the point AB, that's f of AB plus the partial derivative with respect to x at AB times x minus a, and then the partial derivative with respect to y at the point AB times y minus b. That's the equation of the tangent plane. And again, it serves as the linear approximation of f of xy. G of xy, of course, will be approximated by a similar expression, g of AB plus partial x of g evaluated at the point AB, and of course the same thing for g, partial g partial y at AB times y minus b. Okay, so look carefully what we achieved here, and let's see how we can put this in the matrix form. If you look at the f of a and g of b, so that's 0, right? Because AB is an equilibrium point. And what is left is actually a linear system in x minus a, y minus b. In other words, this system, if I look at it in the matrix form, this system that I started with, right, which is f of xy, g of xy, can be approximated by a linear system. In a nutshell, this is the moment when we actually give a justification why we bother with linear systems when in real life we have nonlinear systems. Because in some conditions, provided of course these derivatives exist and so on, this right-hand side can be approximated by a linear system whose matrix of the coefficients is given by these partial derivatives. Partial f with respect to x at AB, partial f with respect to x, y at AB, and second row will be the partial derivative of g with respect to x and with respect to y. So that is the matrix of the linear system that approximates the nonlinear one, a linear system in x minus a, y minus b. That looks a little bit strange to you probably at this point, but that's like a translation, right? I mean, we're not going to bother with this right now, but we can quickly make a change of variables and translate AB to the origin, so that you can put the whole problem in the framework of homogeneous linear systems with 0, 0 at the origin as an equilibrium point. But that's not important. The important part is that in some cases, the stability of the equilibrium point is completely determined by this matrix of partial derivatives. This is called the Jacobian matrix of the functions f of x, g of x, evaluated at the point AB. Okay, so as I said before, there is a caveat. Remember on the previous part when I said if the derivative is 0, we can't draw any conclusion about the linearization. In the same manner, the technique I'm going to show you right now, in the same manner, the linearization that we proceed with here is not going to be applicable if the eigenvalues of this Jacobian are 0 or have 0 real part. So the equivalent of inconclusive situation with f prime of a equals 0 for single ODEs, that inconclusive situation happens here for 0 eigenvalues. Those are borderline cases, and perhaps that's why some weak algorithms of approximation, when you look at the plotter, give you errors, when you have 0 eigenvalues. That often happens, actually, depending on the implementation of that plotter. So let's put this important remark to keep in mind for this class. This technique, the linearization, is not applicable if the Jacobian at AB, because by the way, that's depending on the point itself, right? It's for other point you may not have this problem. So linearization is not applicable if the Jacobian at the point AB has 0 eigenvalues or complex eigenvalues with 0 real part. Okay, so if they are real, they shouldn't be 0. If they're complex, they shouldn't have a 0 real part. Those are the borderline cases in which linearization is not applicable. For the homework, if you encounter this, or in the exam as well, for the purposes of this class, just say linearization not applicable or inconclusive. If it's a homework, you give the answer, try to give the answer based on what the plotter shows to you. And I'm going to give you an example. We're going to finish this lecture with a couple of examples on the plotter, when I'm going to run an example in which you have this borderline case. And in that case, I'll show you that the Jacobian doesn't tell you the answer, but you could figure out the answer on the plotter. There are mathematical techniques, by the way, in which you can do this mathematically, but they are more complicated. You have to go to higher order terms. So just like in the Taylor series for a single ODE, you will have to go to higher order terms to figure out mathematically the stability of the point if the eigenvalues are 0 or have 0 real part. So from this point on, we're going to move on with some examples. Let's go over 2 examples in which the method works, and then we'll finish with an example when it doesn't. So the process is usually to find the equilibrium point, find the Jacobian, evaluate the Jacobian at that point, and just find the eigenvalues. You don't have to solve the linear system, by the way. We care about the stability only, and we can infer that just based on the eigenvalues and the linear classification we just learned last time. So let's start with an example that we can compute quickly. So suppose x prime is equal to y minus x squared plus 1, y prime equals y plus x squared minus 1. So this is my f of xy, this is my g of xy. And in some problems you have to find the equilibrium points yourself. In others it may be given to you if the problem wants to spare you from the trouble of finding the equilibrium point yourself, if it's too complicated to solve. In this case, it's not that bad. If you set this equal to 0 to find the equilibrium point, we can do a substitution. So from the first equation, we get y equals x squared minus 1. And if we plug it into the second equation, that means x squared minus 1 is 0. Don't forget to take all possibilities, all solutions, so x is plus minus 1. And from the substitution in both cases, y is 0. Because y, when you plug in plus minus 1 and you raise it to the power 2, that's still 1. And that means y is 0. Now, that means you have 2 points. Make sure you count them correctly, right? So one equilibrium point is minus 1, 0. Another equilibrium point is 1, 0. So x could be minus 1 or 1, y is 0 in both cases. Then carefully compute the Jacobian, let's call it j of xy, in which you put the partial derivatives of each of these functions. So again, especially if you didn't do partial derivatives before, go slow on this part. Partial x, y and 1 disappears, so that's minus 2x. Partial y of the whole thing is just 1. Moving on, partial x of the second component, the second equation, 2x. Partial y is going to be just 1. So do the Jacobian once in terms of x and y, then you're going to evaluate the Jacobian at each equilibrium point, and then find the eigenvalues to figure out the stability of that point. So let's check minus 1, 0. So we're going to plug in minus 1 for x. Don't forget to pay attention to these double negatives, right? So minus 2 times minus 1, 2 times minus 1 and 1. So the Jacobian at minus 1, 0 is 2, 1, minus 2 and 1. Eigenvalues, lambda squared minus 3 lambda. Let's see, the determinant is 2 minus negative 2. And if I solve for lambda, that's 3 plus minus square root of 9 minus 16 divided by 2. All right, so that's going to be 3 plus minus 9 minus 16, that's minus 7, right? So it's I root 7 over 2. So complex eigenvalues with the real part strictly positive. The linearization works because it's not 0, right? Alpha strictly positive. If you look at the classification, it means that this is a spiral, repelling spiral, right? An unstable spiral. Whatever you want to call it. Unstable repelling spiral. So again, we're going to run this example with, just make sure you check the last part when I'm going to run these examples with the plotter. It doesn't mean that anywhere where you start in the phase plane, you're going to have a spiral point. It's a local property. It means that if I click close enough with the initial point near the point minus 1, 0, I should see a spiraling away behavior of the solution. It's a local property, only if you look at the picture around the point minus 1, 0, because remember, that's a local approximation. Let's check the second equilibrium point, which was 1, 0. Go back to the Jacobian matrix and plug in the point. So minus 2 times 1, 1, and 2 and 1. The characteristic equation is lambda squared. Let's see, the trace is minus 1. So I'm going to have plus lambda minus the trace. And the determinant is minus 4 equals 0. So lambda, if I do the quadratic formula, is minus 1 plus minus square root of 1 minus 4 times minus 4, that's plus 16 over 2. And that's minus 1 plus minus root 17 over 2. What type of roots do I have, or eigenvalues? These are real, one positive, one negative. So one is negative, the other one is positive. That means you have a saddle. So if I click close enough to the point, I should see a saddle type of shape. It's unstable, but in the shape of a saddle, right? I mean, if you look carefully. So it means that there is probably a curve. When you click on it, you may still go toward the point, but otherwise you move away from the point. So if I zoom in close enough to this point, it should look like a linear system with a saddle point at the equilibrium point. So in the second part, in the next part, we're gonna move on with maybe 2 or 3 more examples. And we're going to finish with an example in which, because let's not forget, an example in which the method doesn't work because of a 0 eigenvalue or an eigenvalue with a 0 real part. Stay tuned.